Alright, here's a sort of lengthy exercise about Noetherian rings. Oh, by the way, I used a different notation for my solution. I was using like weird bracket letters to write these. I think like it's like math frac in LaTeX is the thing, and I think capital A. I think my teacher would write it like this or some something. There was like a circle, and then like that, something like this. But I would just write it like this for A, and then B was its own thing. I don't know. It was weird, but I used that. I'm going to try to replace them with normal people letters, but we'll see if I remember to replace them all. So anyways, so we want to prove that every prime ideal in R is finitely generated. No. And blah, 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 blah. Then I is prime. So we want to prove that. So let I be as above, i.e., suppose that I is an ideal in a commutative ring R, such which is not finitely generated, but every ideal properly containing it is finitely generated. So let's take elements x and y to be in I. Then the ideal generated by x and I is the ideal generated by x plus the ideal I, which properly contains I. And that's because it obviously contains I, because the ideal generated by x contains 0, so anything in I is in here, and then it's proper containment because it contains in particular x. And I wrote this wrong. We want x and y to not be in I. So what do we want to prove? We want to prove that if remember the primeness condition is equivalent if x and y are not in I, then the product xy is not in I. And that's the contrapositive of if xy is in I, then either x is in I or y is in I. Okay, so that's where we're going, but here's where we are now. See here. So this is an ideal which properly contains I. So xi must be finitely generated, which means that it's generated by x and then a1 through an for some generators a1 through an. Next, let capital J be the collection of elements R of our ring such that R times X is an element of I. I claim J is an ideal. So we're going to let A and B and J, and R and R. Then AX and BX are in I, and that's because X is in, why is that? That's just by definition. That's what it means for A and B to be in J. These two are in I, so we've got AX plus BX, which is just A plus B times X. No. This product, A times BX, because that's, we want to prove that this not product sum. Wow, it is a little late. I'm still hopefully going to be able to think good enough to do this goodly good. So we want to prove that this is closed under addition, so we want to prove that the sum of a and b is in capital J. So if we apply x to it, then we get ax plus bx, and obviously this is an I since this is a sum of two things, and I is an ideal. Also, see here. Rx is going to be an I because I is an ideal. So if we take R times AX, then this is going to be equal to A times Rx because this is an ideal, which is in I, since R times X here is an element of the ideal. Or, yeah, since it's an element of the ideal and we're just multiplying it by something. So here, this is RA of X, because we're proving. And this means that RA is in J. Here I should have said, so A plus B is in J. Okay, so that's that. And so this means that capital J is an ideal. So let's see here. So now that J is an ideal, the fact that I is an ideal implies that, see here. Since AX is in I for all A in I, we have that I is contained in J. Right? Because if you take anything in I, multiplying it by X is obviously going to keep you in I. So J is an ideal which contains I, but we don't necessarily know that it's a proper containment. But it'll be, we're going to assume that next, or it's going to be part of our next argument. Okay. So now assume contradiction that x times y is in I. We know that both x and y are not in I, and for I to be prime, this must imply that this product xy is not in I. So we're going to assume for contradiction that xy is in I, and just see what happens. Then y is in J. So, but we know that y is not in I. So y is in J set minus I, which means I is contained in but not equal to J, i.e. this containment is proper, and so J is finitely generated, i.e. we can write it as, so here I'm going to use B here, B1 through BM, because I don't want to use J because J is typically used as an index, and I think that would be weird. So anyways, J is generated by this finite collection of elements. Now choose any A and I. then A can be written as Cx plus the sum from 1 to n of Ci Ai for some constant C, C1, and then through Cn. And that's because this ideal I is generated by x and by the AIs. See here. So C times x is equal to A minus the sum from 1 to n of CIAI. So this means that C times x is a sum of products of elements in I, but I is an ideal, and so then the sum is an element of I. Thus, C is an element of J, and so C is also equal to the sum from 1 to m of Cj prime Bj. No, we can use the I. We know that the scope of I is just within this sum. It's here. So C is this for some constant Ci prime. Then A can be written as the sum from 1 to m of Ci prime, and then Bi times x, because the x it's this sum times x, but then we can factor the sum, or we factor the x through the sum, and so it's included in here, plus sum from 1 to n of CIAI. This holds for all A in I. So then all the elements of I can be written as elements of B. So I is contained in the collection of elements generated by B1x through BMX, and then A1 through AN, because any element of I can be written as a sum with these these elements multiplied by some constants. And let's see here. Certainly, the reverse inclusion holds, because each element in each generating element is an element of I. So I is finitely generated. Alright, and this is a contradiction, because we assumed that I is not finitely generated, and hence x times y cannot be contained in I. Because remember here, let's scroll up a little bit. Right, because we assume for contradiction that xy is in I, and we have concluded that xy is not in I. And this holds for all x and y in, for any two elements x and y not in I, we can conclude that their product is not in I. And therefore, I is prime. Alright, there we go. We have finally finished half of this problem. So, now, to prove our is Noetherian if and only if every prime ideal of R is finitely generated certainly this direction holds. And that's because, remember that to say that R as a ring is Noetherian, we've got these equivalent definitions. We've got every properly ascending chain of ideals terminates. We've got every non-vacuous set of ideals contains maximal ones. And we've got that every ideal is finitely generated. So we know that if R is Noetherian, then we know that every ideal is finitely generated. And so in particular, every prime ideal of R is finitely generated. And so this direction is a trivial one. And so, yeah, again, this is a typical case. We want to prove an if and only if, and one direction's trivial and one direction's difficult. And so for the other direction, we're going to prove the contrapositive. So we're going to suppose, instead of supposing that every prime ideal of R is finitely generated and concluding that R is Noetherian, we're going to suppose R is not Noetherian. And we're going to conclude that it is not the case that every prime ideal of R is finitely generated. I.e., we're going to prove that some prime, that there, let's see here, that we're going to prove that we're going to show that there is a prime ideal of R which is finitely generated. So suppose R is not Noetherian. Define cursive I as the collection of all ideals in R. I is an ideal. And cursive I tilde to be all ideals I in this cursive I such that hold on. Oh god. Okay. So I tilde is all elements I in script I such that this is going to be rough. I'm sure it's all, oh god. Are we okay? Are we doing okay? Yeah, okay, I think we're going to get through this. The screen's probably really slowly uploading at this point, so I apologize for that, but I mean, I gotta get these videos up, and I don't have the money to get a super fast computer. So, yeah, there we go. So I tilde is the ideals of the ideals in R such that I is not finitely generated. Okay. So since R is not Noetherian, I tilde is not empty, because if every ideal were finitely generated, then it would be Noetherian. Okay? Now, I tilde is partially ordered by inclusion. So now, okay, so I've brought up this whole partially ordered by inclusion, so there might be something going off in your head like, oh, he's going to do a Zorn's lemma argument, and if that is what's going off in your head, then you're right. So now suppose I0 contained in I1 contained in blah 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 is an ascending chain. Okay. Trying to see if this chain has to be if this chain has to be proper, but I don't think so. Okay, so this is an ascending chain. Let I be the union over all I of these. Oh, this is bad. I. Alright. I guess we're gonna use I as our subscripts for I. That's not pretty, but we're gonna have to do it. Anyways, I claim that I is in I tilde, i.e. that I is not finitely generated. So let's see here. Oh, no. I claim that I is not finitely generated. I.e. I claim that I is finitely generated. So wait. I'm sorry. It's pretty late. I should probably not be doing math right now, but I am anyways. We're going to prove that I is an element of I tilde. I.e. we're going to prove that, here, okay, I see why it is. Because I say I claim that I is in I tilde. And then I say if I is not in I tilde. And so, like, I'm looking at my solution here, and I keep mixing up the two. Okay, so we're going to prove that I is not finitely generated. So if it is, then let I be the ideal generated by A1 through AN. For all I between 1 and n, there exists a natural number ni. Okay, I'm going to adjust these subscripts. I'm going to make it start at 1, because the natural numbers start at 1. So, I can't, it's on the edge of the screen, it's hard to write. So there is some ni such that ai is contained in I ni. So if n is the max of n1 through nn, that's also bad notation, but whatever, then a1 through an are contained in in. But I is a subset of okay. That's not true. My solution is wrong. Okay, so this proves that, let's see here, if A1 through AN is in IN, then the ideal generated by them is contained in IN. And since IN contains I, or IN is a subset of I, because I is the union of all these INs, I equals in, and this contradicts that I tilde, no, this contradicts that in is in I tilde, and thus I is contained in I tilde. Okay, so does that make sense? That's because if I is equal to in, then in is finitely generated, but that contradicts the fact that this is a chain in I tilde, which is all the not finitely generated ones. So this is a contradiction, and so therefore we're contradicting the statement that I is not contained in I tilde, and so hence I is contained in I tilde. And so so each chain in I tilde has an upper bound. This is an upper bound I, which is in I tilde. And so we have a partially ordered set such that every chain has an upper bound. I don't know if chain is the right word. I think it might be. I don't know. Whatever. There might be some other technical stuff going on here, but whatever. But because of this, that's what you need for Zorn's lemma. And therefore I tilde contains some maximal element capital P. Alright, so we want to prove, so what we're looking for is we're looking for a prime ideal which is not finitely generated. And so here's this ideal P, and P is in I tilde, and so P is not finitely generated. So I now claim P is prime. In fact, if Q is in I and P properly contains Q, then by our previous result, we know that Q no, this is if Q is an I and P properly contains and P is a proper subset. Oh, excuse me. And P is a proper subset of Q, then Q is not in I. I say this is because P is maximal. Oh yeah, of course, because Q is just some ideal. So if Q is an ideal and P is a proper subset of Q, then this is not by our previous result. This is by maximality. Okay, I hope my computer is not dying. Please, I'm so close to the end. Just hold out. I'm going to leave this thing running for like 5 minutes after I'm done recording, just because I know like it's going to take like a long time for the last screen to show up. So I now claim previous rhyme, if this and this. Then by maximality, we know that Q cannot be an element of I tilde. See here. by the first, well, not by our first result. This implies that P is prime because P is an ideal in a commutative ring which is not finitely generated, but every ideal which properly contains it is finitely generated. That's exactly what we proved in the first part of this problem. And so now we know that P is prime, and thus R contains a prime ideal which is not finitely generated. Then contrapositively, I'm not going to write it out, not because I don't want to, but because I'm afraid that my computer will explode if I do. So we know that R contains a prime ideal which is not finitely generated. So the contrapositive, so what we've proven is that if R is not, okay, I've said this before, but we've now proven that if R is not Noetherian, then R contains a prime ideal which is not finitely generated. Take the contrapositive of the statement. That tells us that R does not contain any prime ideal which is not finitely generated, i.e., every prime ideal of R is finitely generated. So the contrapositive is that the statement that every prime ideal of R is finitely generated implies that R is Noetherian. Okay, so there we go. And that finishes our proof. And again, I'm going to wait a little bit, let this all show up on the screen. I'll just crop it in, but yeah, there we go. A little bit of a long problem, but we got through it.